Hello and welcome to an introduction to constraint programming. I'm Jacob Allen and I'll be going through this today. Now my voice may be quite familiar because I've done quite a few of these at this point, but slightly differently today. I do not have my face up in the corner. Let's see how this turns out. Hopefully that's not too much of a loss for people. But anyway, yes, today I'll be talking about constraint programming and everything about it. So let's get right into it. So let's start off with the question that's probably at the forefront of all of this, which is, what is constraint programming? So I could go into a long technical definition now of what constraint programming is, but I think we'll save that until we've had a bit of a example to help us with, to help motivate us. So let's start off with a problem that constraint programming can solve. So this is the crystal maze problem, or rather this is the start of the crystal maze problem. What we can see here is we have 8 circles here, 8 nodes, which are all connected together with some number of arcs between them. So this is in a particular pattern, and you may notice that it's quite highly connected. So the crystal maze problem in particular is we need to put a value on each of these nodes from 1 to 8. You can see currently they're all marked with a question mark. And we need to put a value on them, and that value must be distinct across all of them. So one of them will have a 1 on, one of them will have a 2 on, one of them will have a 3 on, so on and so forth, up to 8. But we do have another rule, which is that we also need to make sure that any 2 nodes which are connected by an arc are not adjacent. Now, what do I mean by that? What I mean is, if one of them is a 3, you can't have a 2 or a 4 connected to it. Okay, that's pretty simple. So this originally appeared in the TV show, The Crystal Maze, hence the name, and it was done as a challenge that would take the contestants 5 minutes. They had 5 minutes to solve this. So if you want to have a challenge yourselves, you can pause this video if it's not being premiered, and you can go through and work out this problem for yourselves. Otherwise, we'll continue on. So let's try and solve this problem roughly as a well-informed human would. So we'll start off by considering which nodes are the most connected nodes, because these are going to be the hardest to fill in. So we can see here that the center 2 nodes here are the most connected nodes, and therefore these are going to be the hardest to fill in. So we've got to ask ourselves, what is going to be the easiest way to fill these in? What's going to be the thing that constricts us the least going forwards? And if you think about that a bit, you'll realize that that's going to be either the first value, 1, or the last value, 8, because they don't have values that are adjacent above or below them. So specifically, 1 doesn't have a value below it, doesn't have 0, and 8 doesn't have a value above it, it doesn't have 9. So these are the least constraining values, so we should put them in the hardest place. Now, the way around we put them doesn't matter. So we put a 1 there and an 8 there. So we filled in our first 2 values. Very good. So let's move on to considering one of the other values. So if we look at any of these remaining nodes, we can consider the domain of that node. So we can consider the values that are left that could go in there. So in this case, it's all the values except 1 and 8, except that this is next to the 8 and is in fact connected to the 1, which means that it can't be either of the values which are adjacent to 1 or 8. So it can't be 7 and it can't be 2. So we need to fill in all of these nodes, and in fact these are pretty hard to fill in. So we have these nodes which are slightly easier to fill in on the outside as well to consider. And we can look at the domains for all of these nodes and see what they look like. So here they are. Let's consider these 2 outer nodes now, because they are the outliers from the rest of the pattern, if you will. So it makes sense to assign these 2 outer nodes the next to values because they are connected to they're going to be connected to all the other values that are going to come up in the center that's on their side. So it makes sense to connect the next two values moving inwards, so 2 and 7. And we only have one way around we can put those in, so we'll put them in like this. They're the 2 next to the 8 and the 7 next to the 1, because it wouldn't work the other way around because of the adjacency constraints. So we're now just considering these 4 in the center. Now all of these are pretty symmetric going forwards. We have, obviously they're not the same, but they're all the same problem, and they have pretty reduced domains now, because obviously we can remove the 2 and the 7 from them because we placed those, but now we've also got each of these being connected to 3 other decided nodes. So that rules out all the adjacent values and so on. Though we still have some options. So we can just pick one of these that we're going to look at, and we can't, using just deduction, work out what we're going to put here. So we have to make a guess, but we also need to be ready to backtrack, i.e. if our value is wrong, we have to go back to this point and pick a different value. So we'll pick a 5 in this case. So it meets all the constraints, it's not next to a 1, 8 or 2, and its effects will now roll on and rule out some of the other values for the other nodes. So next we'll pick this one. We've still got to make a guess, so we'll make another guess. We'll put a 3 there. And now we can take that and have all of its effects apply to all the other nodes. So we now rule out the 3 from the others. And we're actually left with a node now that only has one valid value. So obviously we need to pick that value, because if we didn't pick that value from the domain, if we assigned that to the other one, then there would be no value left to assign to this one, which would obviously mean it wasn't a solution. So we need to assign this one to this one here, i.e. we make this node a 4. Now, this leaves us with only one value left to put into the problem. So we only have one value left to put into the problem now, because we've ruled out 1, 2, 3, 4, 5, 7 and 8, so we only have 6 left to put in, and we put it in the last slot, right here, and there we go. We have a complete crystal maze problem. So, as you saw there, we used some simple deduction and some heuristics, i.e. thinking about the most connected nodes, etc., to fill in the crystal maze problem like this. And we'll see that this is a kind of problem that actually very closely is modelled in constraint programming. So let's actually define part of constraint programming now. So constraint programming can actually solve 2 different kinds of problems, but we're first going to have a look at the basic kind of problem it solves, which is constraint satisfaction problems. I.e., this is a problem where we are given a set of decision variables, and for each of those decision variables, a domain of potential values, and then a set of constraints on those decision variables. And we're asked to find an assignment of values to variables such that all the constraints are satisfied. So you can see that's very closely models the crystal maze problem as we just saw it. So, given a set of decision variables, that's our nodes in our little graph for the crystal maze problem. For each decision variable, a domain of potential values, well, when we started out, that was 1 to 8 for each of the nodes in the crystal maze problem. And a set of constraints on the decision variables, well, that was all of the arcs between them, suggesting adjacency constraints, and also the slightly less obvious constraint that we were still applying there, which isn't represented directly in that graph, which is the all different constraint. If we wanted to, I guess we could have represented that by a number of arcs between all of the nodes, but that would just make it messy. So we had our set of constraints, our decision variables, our domain, and all of those together we used to find an assignment of those values from those domains onto the variables such that all of the constraints were satisfied. So we solved the crystal maze problem. So let's now look at a different problem which is also solvable with constraint programming, and specifically another constraint satisfaction problem. this is another really closely mapped problem that you may have actually come across this time, and that's Sudoku. So Sudoku is a pretty simple, in inverted commas there, constraint satisfaction problem, in that it is only using one type of constraint. So if you're aware of Sudoku, it's for each of the rows across, we want each cell to have a unique value from 1 to 9. For each of the columns up, we want there to be a unique value in each from 1 to 9. And for each 3x3 square in our 9x9, we want there to be only one of the values, distinctly again from 1 to 9. So, as you may already be realizing, this is the same kind of constraint as that quote-unquote hidden constraint from the crystal maze problem, the constraint that all of the values have to be different, and in fact, this is commonly referred to as an all-different constraint. So, we're saying that for each of the rows, we apply an all-different, for each of the columns, we apply an all-different, and in each of the 3x3 squares, we apply an all-different, and then the solution should drop out. Well, not quite drop out. So when we apply deduction to work out the values in constraint solving, this is typically referred to as constraint propagation. So we're propagating the effects of a constraint through it. So we've assigned something, or we have some assignments already there, as is the case in Sudoku, and we propagate through via the constraints the results of that to all the domains, and if one of the domains becomes a singular domain, then we can make that assignment, i.e. if there's a single value in the domain, we can make that assignment because it would be the only valid value. So, you may be thinking now that Sudoku problems might actually be solvable just by constraint propagation. Sadly, this is not the case, and in fact, there are some Sudokus that require us to do the guessing and backtracking as we did previously. But, on the whole, the majority of Sudokus are solvable just by constraint propagation. Those that aren't, obviously, we have to have the domains for each of the cells, and you might write down those domains, make a guess, apply the results, and then maybe do some backtracking. And this is actually, again, really close to how a human would solve this problem. So it's very common when solving Sudoku to keep track of the domains of certain cells explicitly in them, rule out values, etc., and make guesses at assignments. So, this is another problem, another constraint satisfaction problem that we see everywhere. And in fact, there are lots of real-world problems that aren't games. We won't go into them really, but they exist and they are solvable using constraint programming. So, I mentioned before that there was another type of problem that's solved by constraint programming, and that is constraint optimization problems. So, what is a constraint optimization problem? Well, given a constraint satisfaction problem plus an objective function, so an objective function is where we are maximizing or minimizing the value of some variable expression, the objective function. So we might want to have the biggest possible value in some particular variable, or maybe we want some series of variables to have the smallest possible value, etc. We're going to try and find an assignment of values to variables such that all the constraints are satisfied, as previously, but now also the objective is optimized. So you may instantly be able to realize that this is going to be a lot less efficient because we have to try all possible combinations which may be optimal, and if we don't have any heuristic for that, that means just trying all possible combinations. But again, this now allows us to open up the set of things we can solve with a very similar set of tools. So let's have a look at a quick example, which I won't go into as much detail as the others with. So let's look at the stack reordering problem. So this is similar to the kind of thing that you have to solve if you're trying to reorder items in a computer's stack. But we're just going to think about it as an abstract stack of things, a stack of blocks. So we have this stack of blocks which are numbered uniquely, and we want to take one ordering of those blocks, say 1, 2, 3, 4, 5, something simple like that, and reorder them so that they are, say, 2, 4, 5, or some subset of them, or some reordering of the original 5, etc. and we have a set of operations we can do on them. I.e., we can swap the top 2 items in the stack, or we can rotate the top 3 items, or we can pop an item off the stack, i.e., we can get rid of one of the blocks from the top of the stack, and then we can't get that back, and so on. We may even start having, like a separate set of variables or whatever that we can store these in. It can be very complicated, but in its simplest form, we're just trying to rearrange the stack using a set of operations. Now, there are 2 things that are quite complicated about this, or at least more complicated than we've previously seen. First of all, it's a sequence of operations, and we actually care about keeping track of that sequence of operations, because the state will change. So it's not just assignments. We actually need to consider effectively an array of states with constraints on them. And importantly for this, we're actually trying to minimize the number of these intermediary states, i.e. the number of operations before we reach our final state, before we've reordered things the way we want them to be. Now, this is a real problem that you need to solve if you're trying to compile code, say, for a stack-based machine, and you need to reorder the arguments of some set of operations. So you need to be able to reorder them. You could use fixed reorderings ahead of time, or you could use something like this to try and minimize the number of operations needed at compile time. So we've now seen constraint satisfaction problems and constraint optimization problems. You may notice that a lot of the time these are referred to by acronyms, but we're going to avoid the acronyms because they are the dreaded 3-letter acronyms, and so very, very overloaded. For instance, constraint satisfaction problem is CSP, which is very overloaded in CS. In computer science, sorry. See the acronyms sneak in everywhere. Anyway, one of the biggest problems with doing constraint programming, and one of the actual points where the effort is spent, is actually modeling the problem. Because we're not telling the computer how to solve the problem, we are instead describing the problem. We're working declaratively. The effort is spent, as I said, describing the problem and not solving it. So the representation of problems and the modeling of problems is a big part of constraint programming. One of the biggest things is the constraints that are on the way that we model these. So for constraint programming to be feasible, we need each of the variables to have finite domains. This rules out things like floating point numbers because they lead to infinite domains. And variables typically in these kind of constraint programming languages have a very strict subset of values that are available to them, i.e. something like integers, booleans, and sequences of integers, booleans, or other sequences, which is very limiting compared to a normal programming language where you have myriad different types available to you. Symmetry is also a really big consideration because a lot of things don't need to be considered so in depth because we can rule out different combinations because they're the same combination really, but via some kind of rotational or reflective symmetry. We won't cover those there because symmetry breaking is very important, but not able to fit into this short of a talk. Right, so last of all, let's have a look at how constraint solvers actually work. Very roughly, this is just how a solver may work, and there are more advanced ways of approaching this. So we're going to use an approach called forward checking, which we'll look at in a second. And we're going to consider all of our variables as nodes and our constraints as arcs between nodes, where they're constraints between nodes. So this is very similar to the crystal maze problem. The crystal maze problem is such a nice problem for this because it is effectively already in the correct form for constraint solving. And we're going to use 2 concepts here. These are the two important concepts in constraint solvers, which are node consistency. So node consistency is that all the values in a node's domain, so all the values in a variable's domain, satisfy constraints on that node. So these are unary constraints that aren't taking into account any other node. And then you have arc consistency, which is given an arc, x to y, given an arc from x to y, for each value in the domain of x, there exists at least one value in the domain of y that satisfies the constraints on the arc. i.e. something is supporting that that value still exists in the domain of that variable, so it's still consistent. And we're going to use the term revision or revise to mean revising, i.e. changing the domains of variables by enforcing the consistency of all of the domains, i.e. looking at arc consistency, node consistency, etc., and removing values that are no longer consistent, i.e. applying a constraint effectively. It's also worth noting that if we run out of values while we're doing revision, i.e. if we reach a point where one of our domains has no values left in it, we know that this is kind of like we've reached a dead end, basically, and we need to go back and backtrack, and if we've already gone back and backtracked through everything, then we're done. We can't find any correct value, and the problem isn't solvable. So let's have a look at the pseudocode for forward checking. So we've got our forward check function, which takes a depth. Now, depth here just means a variable index. So we've ordered all our variables and the domains of all those variables in big D. And for each of our, we're going to consider each of those variables one by one, looking at all the variables that are ahead of them in the list. So for each D in D depth, so for each value that's left in the domain of the current depth, i.e. current variable we're looking at, we're going to assign a value to that variable temporarily while we check things, or possibly permanently if it is consistent. So we go through first assuming that it's consistent, and then we look at each future variable, so all the futures that are ahead of the current variable in our list, and while it's consistent, so i.e. while we haven't found any revisions that lead to an empty domain, we keep going through each of these and we keep revising the arcs from these future nodes to the current node, i.e. we keep revising the future nodes' domains to account for the assignment we've just done. If that assignment we just tried of the first value is consistent and our depth is n, i.e. and we're at the final variable, we show the solution and exit. Good, we've found a solution. Else, we look at the next variable, so we go down recursively. Now, if we come back up from that, it means that we never found the solution down that route, and so we now undo all of the revisions, and we undo that assignment, and we go on to the next assignment, so the next D, the next possible value in our domain. And we keep going through this, and if this function doesn't show a solution and exit eventually, then we know there's no solution, and if it does, yay, we've found a solution. And this is a relatively okay solver. There's a lot of things you can do to make this better, but this will be sufficient, and it's definitely one of the simpler approaches to implement. Now there is a big thing here, which is the revise method here, which is actually doing a lot of work in its own right. It's checking the consistency, node consistency, arc consistency, etc., and it's applying all of these to that graph of values. So it's applying all of the constraints, etc., that we saw. But for the most part, that's the process that's used by a solver. So, conclusions. So we've seen here how constraint solving can solve some interesting problems in a way that's actually quite close to how humans solve those problems. We've also seen that it can solve problems that are quite complicated, it can optimize problems, and it can do all of this relatively efficiently, even if the problems it's trying to solve are really difficult problems. So, what can we take away from this? Well, there are actually a lot of problems which we come across in computing all the time, problems like the stack reordering problem, where you can write a fixed set solver, you can write a fixed set of things, an approach, but actually instead you can use a generic constraint solver and a constraint programming language to solve the problem, usually faster, more efficiently, because people have spent time optimizing these generic solvers. And on top of that, you can represent these problems in a really intuitive way, a lot of the time using these. Constraint programming, therefore, lets us solve a whole class of problems which we would usually consider to be things like tree search problems, but in a much more efficient way by making use of the constraints on the problem itself, by looking at things like the symmetry of the problem or the some of the other constraint considerations of the problem, and it can solve these things much faster a lot of the time than any special purpose solver that didn't take into account all of these things. If you want to write a solver that it does take into account all these things, you can do that, but you might as well be using a generic constraint programming language. And yeah, in general, constraint programming is a really nice and often overlooked approach to solving a lot of things. It kind of, it does have a relation to classical AI, things like tree search algorithms in general, but it's a very nice way of representing these kind of problems, which abstracts away all of that and just lets you think about modeling the problem and then letting the computer solve it in an efficient way. I know I personally really enjoy working with problems with constraint solvers because a lot of the time, once you've fully thought out the problem, you've already solved it, or at least you can already let a solver solve it. So yeah, that's my quick overview of constraint programming, and I'll include some links in the references kind of slide to some interesting resources on it. I'll also link to an actual constraint solver called Savile Row, which you can play around with if you want to and try and solve some problems. It's got some nice examples in there, things like the Sudoku problem, so that you can have a look at all of this and see how it's put together. I'd also like to specifically thank Peter Nightingale, who runs the Constraint Programming module here at the University of York, and who's ended up being the source of almost everything in this talk, or rather, the module ended up being the source of almost everything in this talk. It's a really great module, and if you have the opportunity to take it, you should totally take it. Anyway, that's all from me, and if you have any questions, you can talk to me in Discord after this, if you're watching this as it premieres. Otherwise, thanks very much for watching, and enjoy trying to solve things with constraint solvers.